Hello everyone, I'm Jiasheng Guo. Now I will share our work of Dark-ISP enhancing raw image processing for low-light object detection. As we all know, object detection is a common downstream task in computer vision. There are many excellent methods in this field, but due to noise amplification and diminished contrast for images, their performance decreases seriously in low-light environments. To solve this problem, traditional methods still rely on low-bit depth RGB image processed by some enhanced blocks, but the inherent limitations of this format restrict the potential. In recent years, some exciting methods start to use sensor raw image, that is, a kind of data format has a high storage bit depth and preserves more details in low-light environments. Nevertheless, there is still significant room for improvement, and the potential of the RAW has not been fully exploited. To make up for the deficiencies of these RAW methods, we design a plug-and-play, lightweight image signal processing plugin named Dark-ISP and integrate it into an end-to-end training framework from sensor data to the downstream task. This framework does not require any additional auxiliary data to assist the training process. The framework of Dark-ISP consists of three modules, that is, linear component, nonlinear component, and self-post regularization. Next, I will show them in details. In linear component, the joint parameter matrix P and the corresponding raw image I are served as input. After feature extraction, global and local attention are used to integrate P with that two kind of features Fg and Fl respectively to obtain P'. Then, I is processed by P' to produce RGB image I' as output. In nonlinear component, we predefine a set of nonlinear functions follow two principles below. First, the function must be non-convex to strain the dark regions while compressing the bright regions. Second, each fkx is a polynomial of order k that passes through the points 0, 0, and 1, 1. The network will learn appropriate coefficients to weight the functions based on the output image I' of linear components. Now, let's talk about self-post regularization. The basic idea is to let the nonlinear output U to get linear output P'. Firstly, we can assume there exists an oracle RGB image U star. Given this discrete problem, we get the closed-form solution named as P star. If we want to calculate it, maybe the best choice of U star is the RGB image in normal light condition, but it may incur additional data acquisition costs. This is not what we want. So we use the output U of the nonlinear component as a substitute for U star, and define the resulting approximate solution mapping as P tilde, which serves as a procedural target to facilitate the learning of the linear component. However, notably, U is a function of P'. Obtaining P tilde through this formula is not rigorous, and U is continuously updated during training. Thus, we encourage the directional consistency using cosine similarity for each channel transformation, and activate it after a few epochs at the start of the training. This is the entire process of our self-post regularization mechanism. Now, I will show some experimental results of our Dark-ISP. The results on LD dataset shows that compared to other methods, our approach achieved the best performance, highlighting its ability to better leverage and extract useful information from bare raw data in dark environments. This visualization also demonstrates that, in terms of visual quality, the images enhanced by our proposed Dark-ISP are closer to the ground truth normal RGB images, indicating it has successfully learned the necessary transformations to align raw domain images with the RGB domain of the trained backbone. The experiments on NOD dataset further confirm its robustness across diverse camera parameters. In the visualization on the right, we can intuitively see that our Dark-ISP reliably detects objects in dark regions across both two cameras, avoiding false tips and misdetections. To summarize, we propose Dark-ISP, a novel approach to raw image processing for low-light object detection, which is lightweight, effective, and convenient to deploy. Thank you very much for listening.